to the types of the ANN. So this will be a two series talk. There will be two parts. This is the first part. So since we are covering the details of the neurocomputing structures, therefore it is quite pertinent to go through the types of the ANN. So the plan of presentations shall be types of ANN, then the supervised type, the unsupervised type, reinforcement type, and later on we will find out a few composite types. Now the fundamental concept is that comes from our previous classes, a revision of the previous part, a one-page revision. We found that the neurocomputing structures were primarily designed or are designed primarily to mimic the decision-making capability of the biological brain. It is a non-parametric tool and is quite capable of doing pattern matching, classification, optimization, approximation. We will also find out that it can do a vector quantization and is quite capable of doing clustering tasks. Now, these are quite difficult for the traditional computers. Therefore, these are the tasks primarily meant for the ANN structures. Now, this is how the data flow takes place in the biological nervous system. There will be the biological system, the body. There will be a central nervous system. There will be the receptors, sensory organs. Then there will be the motor organs. Then there shall be a communication from the receptor side to the central nervous system, and from the central nervous system to the effector side. And there will be further a continuous communication to two types of feedbacks. One of it is the internal type, and the second type is the external feedback. So this particular representation of the processing that takes place in the biological nervous system is also replicated in the case of the neurocomputing structures. Therefore, we can summarize that the neural processing system will roughly be confined to the recall process. That is a processing phase through which it can retrieve the contents learned by it or stored by it or remembered by it, and then this particular recall, and then further its classification and regression part is linked with a few form of data processing which are due to the auto association, then hetero association, and finally classification. Now, if we come to the first processing type, that is the auto association type, we find that if we make a neural network learn a few patterns, those patterns shall be learned, and those pattern structures will be retained. So if we give a pattern as a feed that belongs to the classes or the types learned by the network previously, that particular pattern trigger can lead to a decision making. So if supposedly we have a few geometrical structures like a triangle, a circle, and a square that were these were learned beforehand, then if we give a distorted square for its classification, then the neural processing will give us a decision that the distorted square to be a perfect square. So this is one type of learning, one type of neural processing, and this is called the auto association. The second one is called the second type of the neural processing is the hetero association, where we have a linkage between different pairs of the pattern stored. Now, if you give here distorted pattern forms, you may still have a correct decision coming out of it. So you may link a differential pattern mapping. So if you can link a triangle to a circle, a square to a parallelepiped, a cross sign to the letter 8. So if you give here a square or a distorted square, it will be due to the differential in the association generate a rhomboid or a parallelepiped. So this is one more form of processing. Means here we find that differences of pattern can be mapped, or there can be mapping pairs formed between patterns and the responses generated by a neural computing structure. And then the last processing type, or the last form of neural processing, can be classification. So here you can give a set of class codes, or you can formulate a few number of classes. So and if the patterns are linked or are mapped to the classes, once the learning part is complete, despite variations in the feeding sequence of the patterns, we will find a classification decision generated. So this way the neural computing structures work. Now, why we are saying all these things is the fact that on the basis of the processing that the neural computing structures take, we can classify the basic models of the A and N. So here we can have classification in terms of the interconnections, learning rules, and the activation functions that the A and Ns use normally. So if we take the first type, we can have a classification of the A and N based on the interconnections. So we can have a feed-forward type, we can have a feedback type, and we can have a recurrent type. Sometimes the feedback type are used concurrently with the recurrent type too. So the feedback type can sometimes mean the recurrent type too. Now, in the feed-forward type, we may have single-layer structures, we may have multi-layer structures. In the recurrent type, we may have single-layer structures, we may have multi-layer structures. Now, a very straightforward representation of a single-layer feed-forward neural network, as we have discussed in the previous lectures, can be like this. So here, patterns can be represented by small x, small x1, small x2, dot dot small xn, scaled by the weights and summed up there, and then passing on through the activation functions. So this is in a connectionist link. Then so the feed-forward structures, we can have the output and the input vectors represented by this O and X vectors, weights Wij, connecting the neurons layer by layer. So finally, we will have the OI, where the weights will be counted layer by layer, here shown with the count of I. A simple, a common case of the feed-forward network, single layer can be the multi-layer perceptron. We have talked about it in very much details in the previous lectures. So here is a multi-layer feed-forward network. We will find that there will be three layers, least number of 3 layers. One will be the input layer, next will be the hidden layer, and then finally the output layer. And all the layers and all the neurons in the layers are linked with connectionist weights that will be scaling the patterns fed and will be going through the activation functions there in the neurons. Then the feedback type and the feedback network, we will have that there will be a few feed-forward branches, and there will be a few number of feedback branches. So we will find here that the final responses, that those O's will be dependent not only on the patterns fed, small x1, small x2, scaled by the weights wi1, wi2, and so on and so forth, but those will be dependent further on the feedbacks. These are the feedback links. So, and that shall be one more feedback link. So this del there in the feedback link can be a delay or a waiting function or a weight value or a weight parameter. So these will further come back to the from the back end to the front end, and will be contributing in the network's processing. So the feedback tool also here plays a significant role in generating the response of the network. So here we see the role played by the feed forward and the feedback components simultaneously. A very common case is the recurrent neural network. We will be speaking about the recurrent neural network in much details. Then there is one more feedback type that is called the lateral feedback type. So here we find that the feedback of the outputs of the processing blocks is directed back as the inputs to the processing elements. They're in the same layer. So we have a feedback restricted to one layer. So in the previous case, we can find that the feedback can be of the global type. Here in this case, we can find that the feedback can be of the local type. So if a feedback is of the local type, we can call it to be a lateral feedback. A feedback restricted to one layer. Then one more type of the ANN is the recurrent type. So in the recurrent type, as we have just talked about, there will be both feed forward and the feedback paths, and the recurrent networks therefore will be generating a response that is a combination of the present and the feedback components. So both the present pattern fed and the feedback components will be together generating the the responses. So we can find the recurrent networks therefore being quite capable of doing temporal processing. We shall be talking about the temporal processing while we discuss recurrent networks in details. Now the recurrent networks, they can have a single node with a feedback. We can find recurrent networks develop as competitive networks. We can find single layer recurrent blocks. We can find multi-layer recurrent blocks. So these four rough variations we can have with the recurrent structures, recurrent networks. So in terms of connections, these previous types were the classes. Now, since the second classification can be in terms of the learning rule, this particular uh, mm, say method of classification is the most common one, or is the most popularly talked about. So a classification based on the learning rules. So we know that the learning is a process through which the network is made familiar with the patterns. So when you feed a pattern, uh, that particular pattern, when it goes through the network, is supposed to develop a linkage, a mapping with a response. Now, that particular response, till it is generated correctly, the process of scaling the weights repeatedly till the response is closer to the desired one, the weight tuning process will be continued. Now, this particular weight tuning or weight change process that guarantees a response generated due to a pattern fed to it as close to as the desired one is called learning. We have found about learning quite in some sort of details in the previous classes. We can find that broadly two kinds of learning can take place. One will be the parameter learning, and one can be the structural learning. Now, in the parameter learning, we will find that the connectionist weights will be changing, will be tuning. And in the structural learning, we can find that there shall be change in the network structure. Now, while learning, we can refer to one more term linked with the learning, or a supplementary complementary term that is used concurrently, is that of training. Now, this process of making the network learn, or generating a set of weights for which the response is close to the desired one, we call the process to be training. So training and learning, they are nearly similar kind of processes. Now, training or learning in the ANN can be carried out by the use of the supervised method, by the use of the unsupervised technique, or by following the reinforcement route. So there can be therefore three broad types of classification: supervised, unsupervised, and the reinforcement type. So in case of the supervised learning, we can have the raw data coming in straightway for the training part. Now, with that raw data, we will have the labels demarcated. We will mark the training part with labels. So the uh, raw data, from the raw data, we need to do feature selection. So we will be doing some sort of dimensionality reduction. Therefore, we need the feature selection. So feature selection shall be done. So once the feature matrix is generated, we will use that particular feature matrix to train the model, the ANN. So once that part is trained, we will deploy the the trained ANN model. Now these labels are used together with the feature metrics to permit a learning take place. Now, since we are here presenting the labels will work like a reference. Labels will work like a teacher. Now, since there is a reference, Therefore, we call this type of training to be a supervised training or a supervised learning. Now, while we find out the performance of the trained ANN, its performance shall be continuously checked, and if it is not reaching the desired quality level, the feedback will make the feature extraction block perform better and make the training go to the next level, so that we can find the model generate responses as close to the desired one. Now, once the ANN is fully ready, that part now is capable of doing the prediction or is capable of doing the regression. Therefore, during the testing or the prediction part, we can just follow the same blocks as those were in the uh, training stage. So the new data will come here. So we do not need the labels now. Same again, feature extraction, feature vector. We'll feed it to the train ANN, and then we will get the class levels generated. So this is supervised learning. Now, supervised learning is just like a child learning from a teacher. So we will need a training pair that will have an input vector and a target vector being fed to the network together. Okay. So now we come to the unsupervised learning, where there shall be a mixture of the data, all will be mixed together. There will be a clustering going on through this part. Those will be separated out in separate clusters, and then once the clusters are separated out, there will be a manual review. Once it is close to the desired quality, we can have it used or deployed for the testing purpose. So the unsupervised learning shall have no label classes beforehand, so there is no a priori knowledge fed to the network. A self-learning will take place, or a clustering type of mechanism will here govern the learning process. So we can show it like this. There is no reference. So it is unsupervised learning is some sort of a self-learning, self-organization. So there is no reference, or in some cases there will be no feedback paths used to. Network must discover the patterns, regularities, features, and so on and so forth. And while doing so, network might change its parameters. So this is some sort of a self-learning, a self-organization that will go on. Now, there is one more type of learning that is called the reinforcement learning. Reinforcement learning is goal specific. So supposedly there is a fruit. So we want to find out if there is a fruit. So this is a goal driven. So a fruit, you will be questioning it stage by stage. So you will try to find out the type of the fruit. If the response is correct, it will be recorded, and that will be used as a feedback. So it will be considered to be a learning taking place. So that particular learning, if it is recorded to be true, then that one will be reinforced further, so that if that particular fruit comes one more time, its class shall be properly recognized. So there is one such way. Now, here a question comes: why we use the use the reinforcement learning. We use the reinforcement learning if lesser number of patterns are there. We do not have sufficient number of patterns. We are not sure to have a complete representation of the patterns and how those can be linked with the targets. So learning based on lesser details are normally done with the help of the reinforcement learning. So here the feedback path used is mainly for the verification part and not to force some sort of a decision. So therefore the reinforcement learning is a case where there is a sparsity, where there are less number of patterns for a class. Now let's find out some practical network structures that will give us the classes of the ANN based on the training. The first class is the supervised learning. These are the two more popular types: supervised learning and unsupervised learning. Now, for the supervised learning type, we have the feed forward structure, where we have the multi-layer perceptron, the radial basis function, and the probabilistic neural network. And in the feedback type, we have the recurrent neural network. Now, in the unsupervised type, we have the self-organizing map, or the SOM, that we will take up in the next class. Now let's come. Now we have talked about the multi-layered perceptron in great details in the previous classes, so we will not talk about it in this class. We have just here shown a diagram of the multi-layer perceptron to represent a case of supervised learning with feed forward structure. So it is trained with the backpropagation method. Now there is one more type of feed forward structure that is used for the classification purpose, that is called the RBF, or the radial basis function, ANN. So now here it is a network that is based on pure statistical pattern recognition techniques. So it is a structure useful for pattern recognition purpose, but based on the statistical pattern recognition techniques. Then there is one more supervised learning feed forward ANN, that is called the probabilistic neural network, or the PNN. PNN is a feed forward structure that works or is based on the Bayesian principles. So these are the broad classes of the feed forward supervised topology. Now let's talk about the radial basis function. So now we here to start with need to remember, or need to visualize, is a situation where we find that since we are now familiar with the multi-layer perceptron, compared to the perceptron type, the feedback mechanism of the RBF is somewhat different. Now, in the perceptron type network, we find that there is a dot product process going on in the feeding mechanism. So the activation function of the middle layer is based on the dot product, not only of the middle layer, but from the front layer to the mid layer, from the mid layer to the back layer. So between these layers, the feeding mechanism is based on a dot product. So a vector comes in. So x is the vector. So a dot product will take place between the vector and the connectionist weight layer by layer. And then if there is a bias, those will be considered, and will be taking part in the summation, and then we'll go through an activation function. But this is totally different than in the case of the RBF. So here we will primarily focus on a distance factor, a distance measure between the input vector and the prototype vector. So here we need to keep in mind that for the activation functions in the hidden layers, there will be a distance factor. So three parameters. So this phi I will be the radial basis function. Now this will take a vector x. So now this particular phi will consider the norm between the x, that is the prototype vector, and the current pattern vector. So the norm between the prototype vector and the current prototype vector, there will be a distance count, a distance measure. The norm of that will be taken, and that will be passed on through the radial basis function. Now here there will be a center. Three main parameters will come repeatedly. So a center for for the pattern vector small xi, because these will represent a feature vector for a class. So for that particular feature set for the class, there will be a center, cluster center. So that particular center will be required. A distance measure r, that will be a norm of the difference between the prototype vector and the current pattern vector, and the shape of the radial basis function that we will use. Normally there from a lot of basis functions, from a lot of shapes that we have, the Gaussian function is taken to be the basis function. So here is the radial basis function. The most commonly used radial basis function in the radial basis function ANN is the Gaussian function, represented by this bell structure, where there shall be mean and the variance term. We will find that the RBF ANN will have a hidden layer of radial kernels, and there will be an output layer of linear neurons. So there are two layers in a RBF that can play different roles. So we will find that the mid layer will do a nonlinear transformation of the patterns fed. So the resulting hidden space is typically of a larger dimension than shall be the case when we feed the patterns. And the output layer, we find, will be doing a linear regression to do a prediction of the desired targets. So here is a structure. So we will find here these small x1, small x2, dot small xm will be the patterns fed to it. So these will be going to from the front layer to the middle layer. Middle layers are blue ones, and then from the middle layers, they will pass on through the basis functions. They will go to the output layer. So here we will find that the output layer will have linear activation functions, represented by this y is equal to w1 phi1, taking the value of the norm of xi minus ti. So ti will be the target, plus this part will go on for all the cases. So x will be the pattern vector fed here. and T will be the target. Since we have here a supervised classification taking place, so so a target T will be here taken. That particular target, as close as the pattern vector comes while it does the learning, that particular process will go on during the training part. So here we have a mapping from the input side to the hidden side. So this shall be for the network to tune to responses in a local region by means of a radially symmetric function. So here also we have a distance factor coming in. So this particular factor, a comparison between the x vector and a prototype vector mu j, that at that point of time can be a sample mean, will be used for doing the tuning while it is mapping from the pattern feed layer to the mid layer. So choice of the radial basis function, we can have normally that is the Gaussian kernel. We can have the Gaussian kernel with the full covariance structure like this. There is the full covariance structure. So that part will give a better representation. That will lead to a better classification, or a better precision will be also generated, but that will lead to rise in the computation. Or we can have a more simplified structure, that is with the diagonal structure, which will just have the sample mean and the variance term representing the Gaussian kernel. So there should be a small trade-off between the requirements and the computing and the computational demand. So here are a few terms, or a few things that we need to consider. The sigma part will be denoting the spread of the Gaussian function. So it is a bigger one. We will have lot of surface covered. If it is a smaller one, lesser surface area will be covered. But if it is a lesser surface covered, that will take more time to train. So with more number of training, computation will go up, but the final result will be of greater reliability. But if we have a larger sigma value, that is the spread factor, if that is large one, larger surface shall be covered, and if it is covering a larger surface area, we will do the training fast. But if we do the training fast, we might not have the required levels of reliability. Then we have one more mapping, that is from the hidden to the output layer. So here also we need to have a difference, a distance factor, a distance measure, but that particular distance measure now will take part in a dot product with the weight matrix WJK. Now this particular WJK will change, will be tuned by the use of the gradient descent function by following a supervised learning process. So this particular mapping will have further a weight bias term too, and this will roughly be following the gradient descent based training. So the complete structure will look like this. So from the front end mapping, we will have here a thresholding done by the neurons. This will be then the responses of the front layer will be scaled up by the weights, will go on to the Gaussian kernels. There will be a layer of the Gaussian kernels. The Gaussian kernels will be generating responses that will depend on the spread function, on the spread term. Then those will be scaled up by the connectionist weight WJK, and then we'll go on to the. This will be a non-linear transformation mapping. Then we'll reach to the back end, or the output layer, where the prediction will be generated, and that there a purely linear activation functions shall be used or shall be considered. So we can have a few more details. Most common topology shall be three layers. Front end will be scaled up. If we have n classes, we need to have n class classification. Then we need to have n-1 categorical variables. So from the front end, that will be going through a connectionist weight to the Gaussian kernels. From the Gaussian kernels, it will be going through a layer of connectionist weight. Those will be trained with the Gaussian with the gradient descent function. Then that will follow a supervised learning. So a mapping will take place from this front layer, the mid layer, from the mid layer to the back end layer. This part of the process will go on throughout. The mid layer, we know, is based on the Gaussian kernels. Those Gaussian kernels will continuously find out the distance factor between the prototype vector and the test vector, or the pattern vector, and then scale it through the RBF functions. And then in the training process, we will have the weights tuned for a one-to-one mapping from the mid layer to the last layer. Summation layer. Here we will find that the value coming out from a neuron in the hidden layer is multiplied by a weight linked with that particular neuron. If it is passed through the summation layer, that will add up the weighted values and present this sum as the response of the network. There is a bias value of 1 that is multiplied by weight vector, weight 0, and fed to the summation layer. So this particular summation layer will be just prior to the output layer. Now we just will focus on a few network parameters. So we have talked about it, but here we will be summarizing it. There will be centers of the RBF activation functions. There shall be the spreads of the Gaussian kernels and the weights from the mid layer to the output layer. Then we have three different classes of learning, or three different types of learning that will take place in the RBF network. So here we will be talking about those three types of learning. Now, in the first type of learning, here first the centers are chosen. Centers are chosen randomly from the training set. So for selecting the centers, we will roughly or randomly calculate a sample mean from the samples. Then a spread can be selected. That particular spread value is selected from a ratio between the maximum distance between two centers by the number of centers that are there. So here d max by the square root of number of centers that are there. Then comes the activation functions. We will have a kernel represented like this. Phi I will take the values of x minus ti, a norm of it square. Then that will go on through the Gaussian function. So this is the Gaussian function that takes the value. So the weights that will be determined by the pseudo inverse method. So if you have a case of xi and di, so the network will have a form of that type. Y of xi turns out to be w1 phi 1 multiplied by taking the value of norm of xi minus t1 dot dot, so on and so forth. Then we would like to have y of xi taking the value of di, that is the desired value di, such that the weight takes the weight scaling or the weight tuning takes place in such a way that wi phi I wi scaling the value of phi I, taking values of the norm of xi minus t1 dot dot, finally becoming di. So this will be the part linked with the weight tuning or weight scaling method. So if we write the same, that can be also shown in the matrix form, the same thing again. So this weight scaling and the kernels represented in the matrix form can be linked with the desired responses d1 dot dot up to dn. So here it is a more matrix form representation. So it can be rewritten. The steps can be rewritten like this. So here the summary is that we need to choose the centers randomly from the training set, and we need to compute the spread of the RBF functions by the use of the normalization method, then find the weights using the pseudo inverse method. Then there is the second method of learning. Here in the second method of learning, we find a clustering taking place. So in the clustering part, there are 5 stages. One is the initialization, then the sampling, then the similarity matching, then the updating, then finally we have the continuation. So in the first case, we will have some target centers. We will have some target centers and weights given some random value. Now, while we once we do that, we will take a vector x from the sample space, then try to find a similarity match. So this one will be the similarity match. So this particular function will try to find out the similarity match, so that the center is closer to the matrix X. So once we find the specific center, specific cluster center close to the pattern vector X, we can now make variations to the centers defined beforehand by following this particular norm, where tk taking the value t with count of k, taking the value of n plus 1, that is the future value, comes from the present value of tk, that is plus a learning term that is the learning rate or the step size, that will be scaling up the difference between the pattern vector x minus the current value of the centers tk. So here, that is the condition. If k is found to be same as k of x from this particular count, then there is one more condition. If this particular condition is not fulfilled, then tk will take the value, tk future will take the value of tk present. Now this method, this clustering based method will go on continuously till all the patterns are satisfactorily classified. Then there is one more. So here is the summary of the second method, that is the hybrid learning process. Here we use the clustering for finding the centers. Spreads are chosen from the normalization technique, by the use of the normalization technique. Then we use one more technique, that is the least mean square, to find the weights. So the least mean square technique shall be used to find out the weights of the centers, linking the centers. Then there is one more technique. The third method. Here we use the gradient descent method to find the centers, spreads, and the weights. So here we can use the present response and then compare it with the desired response d, square it, and take the half of it. That will be called the value of the e, that is the squared error. Then we take this e and then calculate the gradient descent term del t that we had talked about previously. So del e by del t scaled up by learning term decreasing. This will take, that shall be the value of the centers. Then the spread function, similarly del sigma j, same thing again, but del e now differentiated by the sigma term, and the weights del w, same again, the learning rate, that del e partial derivative of e now taken by the term wij. So this way, the center spread and the weight terms will be tuned. That is the third learning method. Now let's compare the radial basis function with the feed forward ANN. So we will have both have non-linear layered feed forward structures. They both use the universal approximation, and both are used for regression and performing complex nonlinear pattern classification tasks. Further comparison, we find that in the case of the RBF, there will be one mid layer, but in the case of the multi-layer perceptron, there can be many types, more numbers of mid layers. In the case of the neurons, we see that in the RBF, the neuron model of the mid layer is somewhat not same as that of the output nodes. But we have, in the case of the multi-layer perceptron, the perceptrons in these two layers might be similar or might have a common neuron type. Then the mid layer of the radial basis function is nonlinear, while the output layer is a linear one. That is not the case with the multi-layer perceptron. Then we can find that in the case of the activation functions, a distance term will be used with the radial basis function networks, but then in the case of the multi-layer perceptron, we have a dot product between the pattern vector and the weight synaptic weight terms. Then we find that in case of the approximation, we see that the radial basis function will use the Gaussian functions to construct local approximations to nonlinear I/O mapping. But there, in the case of the feed-forward multi-layer perceptron, we see that there is a global approximation to do nonlinear I/O mapping. We see that the radial basis function are used mainly for the pattern recognition and computer vision purposes. So we saw here a case of face recognition database. We have about 100 samples of 10 people at different pages for face on to profile. So these are some of the samples collected from the Sussex database. They are of 25 by 25 size. So so here for the face recognition block of the radial basis function is trained to recognize a single person. In the case of the training, if we want to do a positive recognition, we need to have a number of false recognition too simultaneously, and the training is meant to deal with both these two situations. So here we have a input layer of 25 by 25 size. Then we have a middle layer of P plus A protons, where P will be the mid-layer mid-layer perceptrons that will represent the yes cases, and A will be the no number of perceptrons taken to represent the no cases or false recognition cases. So in the final layer, we have two neurons there. A particular person, a correct class, and the rest shall be representing all the remaining ones. So there is a structure. So here we feed through it. This will be a unsupervised layer. Then here there will be the RBF functions, nonlinear functions. They will go through and generate the responses. That will be done in a supervised form. Okay. So here the training and the testing part shall be just following the steps we have talked about previously. There will be centers corresponding to the yes cases, and a antineuron that will be representing the no cases. Further, we need to have the spread function calculated, as we have talked about previously. Then the weights are determined. So here we have 6 pro and 12 antineurons. Then R value of 0.3. So that way we can classify it. So so now we can summarize this talk, this session, by saying that the ANNs are classified in two broad categories, topology wise, feed forward topology and the feedback topology. The feed forward topology will primarily have the feedback paths. Those can be single layer, those can be multi-layer. And in the feedback paths, we can have there can be a feedback path. The feedback path will be from the last layer to the middle layer, or from the middle layer to the front layer. The feedbacks can be of the local type. The feedbacks can be of the global type. Then we find further that in most of the feedback topologies, there will be a feed forward processing and a feedback processing. Both feedback and the feed forward processing will take place together. Then classification is based on the feedback and the feed forward and the feedback structures. That is the first type of classification. The next type of classification is based on the learning type or the training type. One can find here a supervised training, then an unsupervised training, and a reinforcement type of training. Then in case of the supervised training, we find there shall be a reference, a labeling. We will have a set of samples. We will have a set of patterns, and simultaneously with all the patterns or the samples, there will be a labeling done, and that particular labeling will act as the prior reference that will further work or play the role of a teacher. We see a teacher teaching a kid in the school. So the label part or labeling of the samples play the role of a teacher. Then we find the unsupervised type, where there is no labeling in all situations, since we do not have the labeling, or the labeling, since we find, is quite a tedious task. Therefore, in the unsupervised type, we do not use labeling. There are no prior references. So since there is no prior reference, there is a self-learning, a learn by own type of mechanism goes on. Now this particular process is based on a clustering type of technique. In the clustering type of technique, cluster centers are formed. Cluster centers will be roughly the sample mean. When the samples come in, from those samples, a sample mean will be calculated. Those sample means will form the cluster centers. Now round that sample mean, the rest of the pattern samples will start to group, and this particular grouping is done by determining a distance measure, by calculating a distance term from each of the centers, from each of the cluster samples compared to the cluster center. So this particular grouping will take place stage by stage, and unsupervised learning will thus lead to a classification. So in this unsupervised classification or unsupervised learning, we do not use a prior reference. We do not use a reference. There will be no prior knowledge for doing the learning. But the weight tuning process of the unsupervised learning will also take place through a gradient descent based tuning. it's sometimes based on the least mean squares also, but it is mostly based on the gradient descent learning. Then there is one more type of learning called the reinforcement learning, and the reinforcement learning is primarily a goal driven learning. When we have a sparsity type of situation, when there are not much larger type of larger collection of samples, yet we need to do a learning, we need to do a training, then we do the reinforcement learning. Reinforcement learning is goal driven on a local scale, a maximized a priori probability based on voting is done to derive at a decision. A binary tree type goal specific decision making is done in the local level. A feedback path is used to uh, check or validate the learning. Then that particular validation is used for doing a reinforcement of the learning, but not to reinforce a particular decision. So these three broad classes of learning are used for doing the classification, or to find out the types of the ANN. The most common type of supervised feed-forward structure is the multi-layer perceptron. Then one more feedback topology is the is the radial uh, is the RBF structure, where we use a Gaussian function to be the basis function. There are three broad classes of training for this type of structure. One is based on determining the clusters, cluster center, distance, spread function. The second one is based on a purely clustering type of technique, and the third one is based on the least mean square driven training. Both the radial basis function and the multi-layer perceptron are used for complex pattern classification and vision-based recognition purposes. We find that the multi-layer perceptron has certain plus points, and there are similar plus points of the radial basis function structure. So here is the reference, Simon Higgins' book. And prior to the close, I would like to request the participants to raise a few questions. So I think there are no further queries from the participants. I will share the slides. You can go through the slides. If you have queries, you can send me mail also. My mail, I shall I normally put my details there in the slides. From there, you can send me a mail and collect my details and send me a mail. So there we come to a close today. Next Thursday we will have one more talk on the next types of the ANN. So there we come to an end today. And thank you to you all.